Hey, so I think in the interest of time, we'll go ahead and get started. So it's my great pleasure to introduce Professor Michael Spencer from Morgan State University. Uh, Mike has had a long and distinguished career in semiconductors, covering many different areas. It's our great pleasure to have him here today to tell us a little bit about some of his recent forays into ultra-wide bandgap semiconductors, both the history as well as sort of where things are now. So, Mike.
All right. Thanks, Tyrell. Thanks for inviting me. It's a great meeting. It's great to see Jim again. I remember many electronic materials conferences organized by him and his colleagues where we would spend the night in rump sessions, drinking beer, talking about silicon carbide, and gallium nitride, and which is better. And now we're talking about the next step, which is gallium oxide, diamond, aluminum nitride, and dare I say cubic boron nitride. So I did want to correct one little thing. You can grow silicon carbide by solution, and the reason I'm saying that is we're doing that right here at Paradigm. Yeah, using 3C. My background is basically electrical engineering. So unlike Jim, who went from material science to electrical engineering, I went from electrical engineering to material science. So I'm going to be giving you a kind of an electrical engineer's and an engineering point of view on this topic. So what's to be attempted? I want to give you an introduction to power electronics and tell you where the applications are and what is the ideal device. And some of this will be repetitive from what Jim presented. And then what are the key materials requirements for power electronics, and why the ultra-wide bandgap and ultra-wide bandgap materials are important players. And then finally, I'm going to review, at least give you my perspective on the key materials under consideration. And I'm glad that Jim actually gave you a deep dive on this, one of the newer materials, which is gallium oxide. Okay. So power electronics is the study of electronic circuits intended to control the flow of electrical energy. And the unique thing about these circuits is the power that they handle is many orders of magnitude smaller than the power that they're transmitting. So that the power drops in these devices, whether they be switching devices or diodes, is really quite small. So about 30%, and this is an old dated slide, of the electricity in the United States flows through power converters. As Jim said, we convert from AC to DC, from DC to A levels used to your computer. We convert power that's generated in a non-steady state manner through wind turbines. We're doing all of these conversions. And so the estimates are that 80% of the electricity in the United States will flow through power converters of some kind. So you can see why small changes in the efficiency of power converters are really, really important. So over the last years that I have been around in conscious of electronics, power electronics has been a real revolution. Electricity is the energy currency, and it's the only way to distribute, control, and convert. We've seen more electric airplanes, where the hydraulics is being replaced. We've seen the emergence of the electric car, electric vehicles. This picture is a really old LED-based light bulb, white LED. It doesn't look anything like it looks like today. Wind, solar. And the interesting thing is that we are also seeing the emergence of chip-level power and micropower. So power, I just finished working with a committee um, at SRC, and power has challenges at both ends. It has challenges at the highest power levels, and it has challenges at the micro power levels. And so that's where the new developments are going to come. So power conversion is really an old technology, and it goes way back to Edison. And he not only invented the light bulb, but he also invented the initial power conversion equipment. And ultimately, the company, became General Electric. So we start from there and we move on to this marketplace. So here is a map of where the power utilization is in the conversion industry. And I want you to notice that about 60% of power, at least at the time of saying this chart, is in motor control. Now, in that motor control block, anything under 480 volts is the domain of silicon, and will therefore and forevermore be the domain of silicon. The other blocks where you're talking about now traction control and what Jim was talking about, high voltage DC and power transmission, make up a much smaller marketplace. When we were doing silicon carbide in the early days, we thought we would be lucky if we got to a multi-billion-dollar industry, single billions. Meanwhile, in the LED community, gallium nitride, they were talking hundreds of billions of dollars, approaching trillions of dollars in the solid state lighting market. But the world has changed for silicon carbide. With the advent of electric vehicles, now silicon carbide marketplace is approaching $100 billion. And who knows where it's going to go. And so there is a distinct division between the applications of EV, the applications of high voltage. And right now, companies are concentrating on that big marketplace for electric vehicles. There's also, which is on-chip power. So those are the two marketplaces, and HVDC is a small but important market. So it's important to understand that. So this is also a dated slide. I'll come back to a better one. But I wanted to start making the point. There's several materials properties that are important in what you consider as the ultimate material choice for making these devices. The breakdown field, which is the electric field, and we'll talk a little bit more, it's also known as the critical field. Saturated electron drift, that's more for high frequency devices, but mobilities, electron and hole mobilities also play a role. And there are a few other things. Key these days is thermal conductivity. And one of the biggest challenges with gallium oxide, and one of the things that they're going to struggle with, is how to cope with the fact this is a very low thermal conductivity material. I can't stress enough the importance of getting heat out of devices. So in addition to breakdown and so forth, it is really important to get the heat out. I'll show you this in also a dated slide. This is a dated slide. People were contemplating the first application of silicon carbide in the Prius. And interestingly enough, when you looked at the Prius, the original Prius, it had a cooling system for the electronics and a separate cooling system for the motor. That's because silicon electronics had to be cooled in order to operate properly, and they were working with IGBTs, which switch very slowly. There are two types of devices. There are minority carrier devices and majority carrier devices. And minority carrier devices tend to have transients and switching losses that force it to switch at slow frequencies. So The advantage for putting silicon carbide in was a weight reduction and size reduction and a speed increase all over silicon parts. Higher switching speed because you went from a unipolar device to a unipolar device from a minority carrier device. Smaller speeds because you could get smaller size because you could get the heat out and weight. And the losses altogether were reduced by up to 90%. And even though at that time silicon carbide was more expensive, it was still a significant reduction over silicon. So what is the basic device? What are you doing in a power circuit? What are you doing? So what you're doing is you're sloshing the energy between either magnetic fields or electric fields. And as you slosh this energy, you are then converting it either voltage-wise or current-wise by magnetics or by clever arrangements of circuit topology. So the basic thing you need is something to control how this happens. Now, inductors and capacitors are lossless devices. So you don't have to worry too much, at least ideally, what's happening with them. And transformers, for the most part, are pretty lossless. But you do need a switch. So if you could, you would love to have an ideal switch. An ideal switch is one where when you close it, it has zero resistance. And when you open it, it has no current across it and infinite breakdown voltage. So here's our ideal switch, right? In the on state, it's perfectly parallel to the y-axis, and off state perfectly parallel to the x-axis. But here's our real diode. Our real diode has resistance as given by pointer here. Does this work?
It is.
Yeah, just press it here. Okay. So it has a real resistance, right? It's this slope. It has an on knee of some sort. And so the on knee and the on state resistance are our basic loss. It has leakage current, right? There's leakage current in the off state and a finite breakdown voltage, not an infinite. So here is our real device. And this is what we have to work with. And the same thing with a transistor. Transistor has a resistance in the on state and a active region. Switching is not linear, it's nonlinear, as opposed to the ideal transistor. Okay, so a typical circuit, a very common circuit, is called an H-bridge. And in this circuit, you can either actuate a motor winding or a transformer. And there's some other boost buck circuits. But in the H-bridge, which is used, and I should say circuit topologies in power electronics are extremely mature, and they're not going anywhere. There's not much innovation possible. But what the materials community needs to do is to make a really good diode that provides a pathway when this motor is switched with the storage of energy here needs a way to come back, and this is called a flyback diode, or to provide the switch. Ideally, the switch would be a MOSFET, a power MOSFET, but in silicon, you have to use IGBT. So this H-bridge consists of 4 switching blocks, which is very, very standard. So that's what we have to make. Okay, so the ideal switching would be for you to turn the voltage on, and the current would go down, turn the voltage off, the current goes up. But in reality, there's always going to be some sort of switching losses. in the circuit. And this can be even more complicated when you deal with real inductors. Okay, so the power loss is expressed in terms of I times V, and the forward voltage is going to equal the diode drop plus the IR drop times the duty cycle, the time that it's on. In reverse, in the power off situation, the power dropped is equal to the leakage current times 1 minus the duty cycle. The leakage current can be small, but the voltage is quite large, so the power drop can be significant. One of the challenges that Jim mentioned was you make a low leakage Schottky diode. And how do you prevent things like tunneling currents to increase the leakage with time? Because that will affect your power loss. Okay, the analysis, and I just want to go over this again so that you'll maybe get a better understanding of this ideal rectifier that Baliga analyzed. The ideal rectifier is analyzed in terms of a diode and a drift region, a resistance due to the drift region. So this is the ideal diode. It's the, here the drift region is modeled. This is the anode of the diode, and this is the substrate it's grown on. Now, it turns out that although this is just a diode, this analysis rings true for PN junctions as well as Schottky barrier diodes. This is a good analysis. It also is okay for PIN devices, provided that you understand the breakdown mechanism is punch through. It also says a lot about the performance of a vertical power MOSFET, because the blocking is again blocking with a PN junction diode. So it is a good approximation for a lot of things. Okay, just a reminder of our basic diode device. So let's talk about the device in the off state. Most of you have had a first level course in device physics, and you know this is the forward bias device where the barrier is lowered, and this is the quasi-Fermi level approximation. And this is the reverse bias junction where you increase the barrier, and in the abrupt junction approximation, there's no debye-tails. The depletion region increases with reverse bias. Okay, so it's a solution. The mathematics is a solution of the Poisson's equation. You have a certain charge, which you integrate to get the electric field, which you integrate again to get the voltage. And the important thing is that you have a depletion region, which goes as the square root of the built-in voltage plus the applied voltage related to the dopings. And that depletion region will determine your field. All right, so if you have a one-sided junction, which is the world we live in most of the time, this also applies to a Schottky barrier, the field is triangular, and you can approximate the depletion as into the low dope, as occurring mostly into the low dope side. So the voltage, the maximum voltage that is allowed across the diode is related to the maximum depletion region times the doping 1/2, and it's the square power here. Okay, so we are concerned with how much voltage you can get across a diode. And the limiting factor is a process called impact ionization. Right? And impact ionization occurs when a carrier, which is accelerated by the electric field, inside the p-n junction region, has enough energy to create an electron hole pair by an impact process. Interestingly enough, as a sidebar, conservation of momentum and energy determines that there's a certain minimum energy for impact ionization, which is about 3/2 the band gap. But we are interested in this process continuing. So one electron creates electron hole pairs, another one that creates that electron is accelerated, creating more electron hole pairs. So you have what's called a multiplication. So this process of impact ionization is characterized by something called the impact ionization coefficients, which are represented by the Chenoweth equations in terms of an A and B parameter. These impact ionization coefficients are very, very sensitive to the electric field, and they are really a function of the material. So you can see the impact ionization coefficients for silicon, and here vastly different is the impact ionization coefficients for silicon carbide. One of the things I want to leave you with is that very few of these impact ionization coefficients have been experimentally measured, because it is very difficult to get a device that will perform at the regions where you want to measure it at without leakage. Leakage could occur through dislocations, all sorts of imperfections, microplasmas. So when you see these very nice charts that predict the breakdown voltage, they are usually guesses. Sometimes they're informed guesses with some theory, but they are of silicon, which we absolutely know, and silicon carbide absolutely know for very, very good measurements. And I don't know, Jim, do we have the same information for gallium nitride now? I haven't followed it. Do we? We don't know it yet. Halfway. So there's usually one definitive paper that gets published, which everybody accepts as the thing. So we don't know it for gallium nitride, aluminum nitride. So bear that in mind when you're making the evaluations. If you know what the ionization coefficient is, which goes approximately as e to the 7th power, it will be possible for you to calculate the multiplication factor and predict the breakdown. So here is the equations for characterizing the multiplication as you get, in this case, whole current, whole initiated multiplication. These are the equations, and with math, you can see that the multiplication coefficient is a function of these ionization coefficients, which are in turn a function of the electric field. So if you know the ionization coefficients, you can solve for the breakdown condition, which is this one for hole-initiated processes, or this one for electron-initiated processes. Often, we make life easy for ourselves and say, well, maybe these ionization coefficients are equal, and then it becomes a simple integral. For silicon, there are some approximations. So in calculating the critical field, you basically solve, in this case, the simplest case. Here is the ionization coefficient, and the electric field is varying in the classical triangular field formation, so you can calculate the critical field. When you actually do the calculation, you can see that the critical field has some variation with doping, and these are simulations. And here is the critical field of silicon, which again has some variation with doping. But notice the dramatic difference between the critical field of silicon carbide and the critical field of silicon. There is a lesser difference between that and gallium nitride, and this is a matter up for question. So this is an old viewfoil, and so people may say, okay, there's more change here. But the takeaway point is we had a dramatic change in the critical field of silicon carbide versus silicon. Once you know the critical field, then you can predict the breakdown breakdown voltage versus doping. So here is that calculation for silicon, and here is that calculation for silicon carbide. Right. So this becomes the basis for why these two materials and others like gallium oxide become so important when you go to the higher breakdown voltages. We remind you that the maximum depletion width at breakdown will be a function of doping. So at, say, breakdown at a doping of 10 to the 15th, there will be a breakdown voltage at that doping. This is given by the maximum field, and this chart, or this nomograph, shows you what the maximum depletion width is for silicon at breakdown. So 100 at 10 to the 14th, 100 microns, and the maximum field over here would be given by the nomograph. Okay, going back, reminding you this is our ideal rectifier. And again, reminding you things you probably already know, that the resistivity of any material, this one for silicon, mobility, and the number of electrons and holes, and the mobility itself is a band structure dependent property. So we expect the mobilities for are much superior abilities for silicon carbide due to a smaller, longer mean time between collisions and a smaller effective mass. So we know ionization coefficient is a materials property. We know mobility is a materials property. And finally, as Jim mentioned, doping is now a materials property because doping depends on, in this case, the difference between the donor level and the Fermi level, or the acceptor level and the Fermi level. So the depth of the donor or the acceptor states is also a materials dependent property. So these three materials dependent properties will then get put together to determine the calculation which everybody shows. All right, so here is the calculation that Jay Baliga did. This is the on specific. Should be emphasized that this is not the resistance, but this is a specific on resistance. So this resistance works for any device. All you have to do is supply the width of that device. And it is a function of the breakdown voltage and the critical field. So this relationship between breakdown voltage and specific on resistance is the thing that everybody presents. Okay, so let's look at it again. And I want to emphasize that if you have somebody giving a different presentation, they may argue with you. And it always happens. And I will not go into that today. This is where it was at the state that this viewfoil was made. So here's silicon, and I don't think anybody would argue with that. Probably people are not going to argue with too much about silicon carbide anymore. But the positions of gallium nitride, diamond, and aluminum nitride, they can move around a little bit. So at a given breakdown voltage, if you move over to look at what, I'm sorry, at a given on resistance, did I lose it? I think my pointer died. Never mind. At a given on resistance, when you check what the breakdown voltage is for silicon, it's about 10 to the 3. When you check that equivalent resistance for silicon carbide, it's 10 to the 4. So there is an improvement almost 200 times in on resistance and breakdown voltage going between silicon carbide and silicon. So this is what Jay Baliga contributed. This understanding that you could get so much more value by going to a wide bandgap material. The intrinsic region is, the intrinsic idea is the maximum depletion region that you need for a given breakdown voltage will determine, together with the doping, what the on resistance is. So you can get the same breakdown voltage at a higher doping in silicon carbide than you can in silicon. There's another thing that I wanted to just point out, and this relates to another idea. As you go to a wider bandgap material, as the temperature increases, you will create more intrinsic carriers. At some point, you will lose the ability to control the semiconductor. The temperature that happens, that maximum temperature, is dependent upon the band gap. So for example, in the case of germanium, you get an intrinsic carrier concentration of about 10 to the 15th at 400 degrees C. You've already lost control of the material. In the case of gallium arsenide, at 400 degrees, you would have a intrinsic carrier concentration of 10 to the 10th. So you haven't lost the material. So it is a wide band gap, gives you high temperature operation as well as high power operation. Okay, so let me talk about thermal issues, and I'll give you an example. Every practical device that you have, every practical power device that you have is going to be connected to a heat sink. That heat sink can be modeled by the thermal conductivity of the various parts of the heat sink to the ambient temperature, whether that's water-cooled or air-cooled. So here is a resistance, thermal resistance model of a heat sink. And the power dissipation is going to drive the energy through the thermal resistance of the junction. So what happens as the Schottky barrier rectifier, which is this case, heats up? As it heats up, initially the power dissipation is going to go down because the on voltage will decrease as the temperature increases. So the power dissipation will go down initially. However, at some point, leakage currents in the Schottky barrier diode become high enough so that the power increases, and the current density times the on resistance also begins to cause the power dissipation. So at some point, there will be a turn or okay.
What happened, Mike?
I don't know.
It was
The
going
gremlins are getting me.
it was going so well.
I know.
And I was back.
All right. So there's a minimum power dissipation, and now the temperature is going to start rising again. The resistance, the thermal resistance between the junction and the ambient will determine this straight line. So there is going to be a maximum operating point after which this whole situation will go into thermal runaway. So one of the things that will determine where that maximum operating temperature is going to be the thermal resistance of the material. So thermal resistance has gotten to be such a big issue in high power microwave devices, high power devices, that it is a big influencer of the materials choices. So other issues, minority carrier lifetime. For those materials which have direct, indirect band gaps, you can have a long minority carrier lifetime. And that means that, that you can have minority carrier devices. Minority carrier devices always have higher power handling capabilities because of the ability to make certain kinds of structures. So finally, there's a list of other materials related issues. Substrate, whether or not a substrate exists. I think Jim talked about this, the substrate viability, the cost. How big is the substrate? Electron and hole mobilities, which determine the Baliga field figure of merit, and the saturation electron velocity. All right, so with that, I'd like to finish by talking about each of the materials, which Jim has already talked about, gallium oxide. I'm going to talk mostly about the rest of them. Okay, so here's a summary of all of the materials. You notice gallium oxide is not on the list, but all the materials with the exception of gallium arsenide, silicon, 4H silicon carbide, gallium nitride, aluminum nitride, diamond, cubic boron nitride. When we talk about gallium nitride, we are really talking about gallium nitride and the low X aluminum gallium nitride alloys, because they usually come, the devices are usually come as heterojunction devices. When we talk about aluminum nitride, we're talking about aluminum nitride and the high X aluminum nitride, nitride devices, because aluminum gallium nitride devices. And then we're talking about diamond and cubic boron nitride. All right, so silicon. Historically, the workhorse material, the industry choice for 480 volts and below. Notice, however, that as you go to the higher powers, you're switching from the silicon MOSFET to the IGBT to something called a gate turn-on thyristor. This is a silicon-controlled rectifier. All of these, this one, and this one are all minority carrier devices. They're slow and they're difficult to operate with control circuitry. The most versatile device is the power MOSFET. The thermal conductivity of silicon is good. The substrate is incredibly low cost. Manufacturing, everybody knows how to do it. The oxide for the MOS device is silicon dioxide. It's the best in the business. Silicon carbide. Silicon carbide is available in 3 polytypes, but the commercial one is 4H silicon carbide. This is the Randell notation, which explains 4H silicon carbide, and you can see how it's neither pure hexagonal nor pure cubic, it's not pure hexagonal. It's either cubic or something called alpha, which is a mixture. This is 50% cubic hexagonal, and this is 33% cubic hexagonal. Okay, so it has a higher critical field and thermal conductivity than silicon, which is why it was a big success. The mobilities are comparable to silicon, has a shallow N-type dopant, a relatively deep P-type dopant, but still operational. And the substrate technology is rapidly maturing. The costs are going down and the size is increasing. 6-inch silicon carbide is quite available. 8-inch has been done in the laboratories. When the market demands it, that'll be ready. And the power MOSFET has been adopted by industry. So industry has embraced silicon carbide for discrete device technologies greater than 1,200 volts. Industry has embraced silicon for device technologies less than 480 volts. That's where we are today for discrete devices. Gallium nitride is usually made competitively on a silicon substrate, although single crystal GaN substrates are becoming available. They're really quite immature and costly. But right now, you can grow good quality gallium nitride devices on silicon substrates, but it's really not just gallium nitride, it's gallium nitride and aluminum, low-X aluminum gallium nitride using polarization induced doping. This device is a lateral device, which causes problems, but is workable. That has a comparable field to silicon carbide, some say a little better, comparable thermal conductivity to silicon. Substrate technology is difficult and expensive, so it appears on silicon substrates. P-type doping is challenging, but you can do it in gallium nitride with magnesium. It's a direct band gap material, so no minority carrier devices are allowed. And there's no viable oxide, so no MOS devices are really allowed. Industry has embraced on-chip device gallium nitride technology on silicon, and it has a great future. These devices are being put on right next to silicon MOSFET technologies, and what am I saying is wrong? Okay.
That's what's happening.
Oh, okay. Thanks.
Yeah.
All right. And there's a great future. As a matter of fact, people are trying to understand how to make gallium nitride-based controllers on chip. So that not only do you have the switching devices on chip, but you also have the controllers on chip. So industry has spoken about gallium nitride technology, and it's going great guns, and market is going to be big. You see gallium nitride probably in the power blocks of your Apple phones, iPhones, things like that. And his colleague Umesh Mishra was one of the principal technologists who started the company Transform. Yeah.
So say that there's no MOS devices because there's no oxide.
Yeah.
And are there any insulating nitrides or anything that work here, or is that all something to explore?
I think the oxide on the deposit oxides on the nitrides, people are speculating that might be something interesting there. But there's no native oxide that works. Yeah. Gallium oxide's a mess. Okay. All right. So aluminum nitride and high aluminum concentration alloys. So if you are working at 85% aluminum in aluminum gallium nitride, your donor states are much shallower, and they're functional. The reason why the shallow donor state in aluminum gallium nitride goes to a deep state in aluminum nitride is an interesting story. and some revisions are being currently written in the literature as to why. But I buy into the first explanation about DX centers, which goes back to Dave Lang and and Chris Vanderwaalle.
Just wants to interrupt you. man.
I know. It is feeling my negativity toward gallium oxide, and it's just turning the machine off. Somehow Jim's Zen powers are working. So anyway, this is a question that's actually interesting. However, the problem is once you go to a 85% alloy, then you have stress issues when you try to grow it on aluminum nitride. So it makes the process very different. P-doping in aluminum nitride is very difficult, if not impossible. Aluminum nitride wants to be an insulator, and so vertical devices, which are a big deal in the device community, we would like to have a vertical device. We will accept lateral devices if we have to, but we really, really want vertical. GaN, with the new substrates, will try to get vertical devices. The critical field is higher than silicon carbide and comparable to diamond. And I put question marks because I told you earlier, until you actually measure it, it's just speculation. There's some questions about diamond actually, and people are trying to measure that because it doesn't seem to live up to some of the hype on the critical field. And also no MOS-based device technology. I am not aware of any commercial power devices based on aluminum nitride or high-X aluminum. So diamond, if you want to talk figure of merits, diamond blows everything out of the water in terms of figure of merits. And that is due to this extremely high thermal conductivity and the predicted critical field. The mobilities of electrons and holes of diamond are very high. However, the substrates are extremely small and expensive, and the dopant levels are extremely deep. So in order to actually dope diamond, you have to put in enough dopant so that the band structure gets distorted and the level, which is 0.375 of the N-type, of the P-type dopant, starts to move closer and closer due to these large amounts of doping, and the state becomes banded. So effectively, you are decreasing the energy. That happens because of the extreme solubility of boron in diamond. Now, having said all of that, there is still a great interest in diamond because of this. I can't stress enough, the thermal conductivity of diamond is game-changing. And finally, I'm not going to talk about gallium oxide because Jim already did. And finally, cubic boron nitride, which is my personal choice. It's the most speculative material in the world. I have a theory that says that if you're in a place which doesn't have many resources, and you're not sure you can compete with the pace of development in devices or even materials that are sort of leading like gallium nitride, you have to take a few risks. And cubic boron nitride is an interesting risk. It was first discovered at the same time as all these other wide band gaps, which is silicon carbide, aluminum nitride, were all electric in the 60s. Cubic boron nitride, same time. It is a high pressure, it is the high pressure stable phase of hexagonal boron nitride. And it has really great properties. We think, guesstimations. We think, so at least somebody said it could have an 18 megavolt critical field. The thermal conductivity is almost as good, perhaps better than diamond, we think. Most interesting thing is the dopants for both N and P type are relatively shallow. And finally, the mobilities, which are all estimates, are not horrible. Also, cubic boron nitride is an indirect material, so minority carriers are possible. Diamond, cubic boron nitride, aluminum nitride, and silicon carbide all have substrate technologies. But the challenge is, while diamond has demonstrated a seeded growth technology, to date, this Tyrell tells me wrong, something is new, there's been no seeded growth of cubic boron nitride. It, however, grows in the same way as diamond. So you have hexagonal boron nitride, you have some sort of flux solution, an alkaline flux, and you're growing at temperatures around 2000 degrees to try to get into the stable regime for cubic boron nitride. Okay, so takeaways. Power electronics is key to the economic health and security of the country in so many ways. New applications at high power levels require wide bandgap and ultra wide bandgap materials due to their better materials properties. There are several candidate materials, and each of these materials I've tried to convince you of offer many advantages, but also several challenges. So there's no perfect choice right now. In order of maturity, my words, not necessarily the field. In order of maturity is silicon, silicon carbide, low X aluminum gallium nitride alloys, high X aluminum gallium nitride alloys, diamond, and cubic boron nitride. Doping issues in all materials save silicon. Gallium oxide may be disqualified by low thermal conductivity, and we have a lot to learn about cubic boron nitride. So that's my story. Thank you.
Couple questions?
Yes, sir.
So I really appreciate your skill for nitride. Well.
Okay.
And so, looking back at the phase diagram, see that the boron nitride at pressure is supposed to be phase, but
Yeah.
we don't see that.
Yeah.
Do you have any comment as to why you think that could be the case, or?
What the question is, we don't see the stable phase of cubic boron nitride?
At lower temperature pressure beyond the gigapascal range.
Well, how should I answer the question? It is possible to grow cubic boron nitride in that pressure range, right? You know that, right?
Yeah, no. What I'm saying is that, so if the phase diagram.
Yeah, which by the way is not gospel. I have seen people make arguments that this is not the true phase diagram. But go ahead.
Yeah. So that's what, like, this phase diagram, I think this isn't necessarily the most current, but it's definitely like what I think in the literature it's more or less like beautiful. I actually want to get like.
So why can't you grow? So I think your question is, why can't you grow cubic boron nitride at 1200 Kelvin? Yeah.
Well, I'm not sure the experiments have been done, right? So we've all been trying to grow cubic boron nitride on diamond substrates, right? I mean, that's been the vehicle of choice. We haven't had to try to grow cubic boron nitride on a cubic boron nitride substrate as of yet.
Well, so we've tried it.
And not happening? Well, I should talk to you a little bit. Because I'm really interested in that result.
It's basically, yeah. Exactly.
Yeah.
Why? I don't know.
How, may I ask you what technique you're using to grow it?
Flux.
A flux approach? At what, low pressure or high pressure?
Low pressure, so below, like, below 10.
Okay, all right.
Yeah, it's just, we're excited about the material as well.
Yeah, no, our approach has been more in the epitaxial phase, the epitaxial regime, where we're trying to use, I should say, epitaxial tricks to try to etch or remove the hexagonal phase and allow the cubic phase to grow. And there's been some success there, but I'm interested to hear more about your approach. Yeah. Yep.
Any other questions? Okay, well, thank you, Mike.
Okay.